So yes, as an organizer committee, I invited myself to be a keynote, so thank you for that. And so you can see that I have the CMI logo, Critical Minerals Innovation Hub, and I'm the focus area lead for enhancing and diversifying supply. So as a professor, I wear sometimes the CMI hat. If you were at dinner last night, you heard Tom Lagrasso, who was my boss at least half the time, as the director of CMI, say that he's also a faculty member at Iowa State, so obviously I'm a faculty member here at Missouri S&T. He doesn't have tenure, I do. So I am representing Missouri S&T today as a tenured faculty member who can say whatever I want. So those opinions expressed by myself are not those of the federal government, nor Department of Energy, nor Critical Materials Innovation Hub. Okay, with that said, let's talk about the critical mineral recovery challenges. I'm a hydrometallurgist, extractive metallurgist, sometimes an attractive metallurgist, and so these are just my thoughts on if you're looking for research ideas, here's what I think, okay? So first of all, I teach an introduction to extractive metallurgy class, and I always start out teaching young metallurgists, we're Americans and we like stuff. We like to consume lots and lots of stuff. This is the Mineral Baby. The Mineral Education Coalition does this every year. They haven't done it for 2025 yet, so this is the 2024 numbers. And you can see this is the average consumption that you and I as Americans consume over our lifetime. If you want to know, I've been tracking this since I started as a professor in 2005. When we had the great financial crisis of 2007, actually our consumption went down by almost 20%. I guess Goldman Sachs took all of our money and we couldn't buy the concrete anymore. But essentially, we went down 20%, and we've been holding basically steady, maybe up a few percent a year as we've started to do things. And I'm very curious to see what the new numbers are, or maybe next year, because of all of the infrastructure bills that have happened. Because, of course, I don't personally consume 61,000 pounds of cement in my lifetime, but I sure do drive on the roads and enjoy the buildings that we have. So we consume a lot. And as technology has gotten better and more advanced, then the number of elements that we use goes up. And I'm sure if you've, in the space of critical minerals, you've seen how many elements are in a cell phone or whatever. And so basically the number of elements that we need to generate the things that we want and consume keep going up. It used to be in the old days you just needed concrete and some iron. That if you want to know why we're Missouri S&T or Missouri School of Mines is here, is because we had an iron mine that's over there by the trout park. We had the first blast furnace west of the Mississippi. And so we were a critical source of materials, which is why we had a fort, two Civil War forts here, because we were the terminus for the railroad, and also because we needed a military presence in the area to protect the lead mines and the iron mines, which are important for steel rails and musket balls back in the day. And so we've always been here as S&T about critical materials, about supplying the needs of the nation. But those needs keep getting more and more diverse, which allows for very small markets to be manipulated. So this is an image I pinched from the Glencore investor packet in 2016. So Glencore is one of the largest non-ferrous metallurgy mining companies in the world. They trade a lot of metals. And they had a consulting firm that estimated how much more copper, nickel, and cobalt would be needed as we have electric vehicle build out across the world. In case you were wondering, you can see in the upper right, the vehicle sales were projected by 2025 to be 10 million per year. Last year we hit 17 million, so the projection is not that bad off. And they were projecting, based on infrastructure need, grid storage, and so forth, you can read the slides, how much more copper, nickel, and cobalt they were estimating the world was going to need. And so you can see I've plotted, or in the text is copper, nickel, and cobalt, and what the world production in the mines were based on USGS numbers in 2016. So if you go out to the 2030 numbers over there on the right, you can see how much increase. And the one that always scares us, everybody knows, was cobalt. That's why everyone is concerned about cobalt. But you can see that basically since the last numbers coming out of USGS are the estimated 2024 production of copper, nickel, and cobalt are there in bold. And if you quickly do the math, because I know we're scientists in the room, so you're already doing the calculations in your head, we're doing really good as a world. We're meeting these things, or exceeding them. The amount of nickel that's being produced, the amount of copper that's being produced, has met the forecasted need for the electrical vehicles and beyond. So, is it a supply problem or a location problem? And as we talk about critical minerals, we've talked a lot about critical materials and minerals in this conference, but I think we all know that the elephant in the room is it's not necessarily the supply. If everyone played according to our rules, we'd be perfectly happy. But there are people who don't play according to our rules. And notice I used our rules. I'm not being judgmental too much there. And the issue is that there are certain countries that dominate the world because geology is not democratic. Right? Geology is wherever Mother Nature put the mineral deposits that are world class. Right? We have world-class lead deposits here in Missouri. Did we put them there as a nation? No, we inherited them when we moved here. And so you can see these things, and of course the issue is that the Indonesian nickel market has just exploded, the mines there and the processing plants. And of course the issue is that the same country that dominates copper and cobalt also dominate nickel and cobalt by ownership of mines in those countries. And so the elephant in the room, of course, is always China. When you look at the minor elements, and that's what we used to call them in metallurgy, if you go back into the 70s and 80s, in the 19th century or 20th century, you see conferences on minor elements. That's what we called them, right? Minor elements. They were just these things that were there in small quantities, and you might recover them because, well, actually, as a metallurgist, most of the time you recover these minor elements because it's an effective way to dispose of an impurity. So let's sell it, make some money. We probably don't make a profit, but we can get rid of it. Okay, and so the interconnected circle here, and I think someone showed it yesterday as well. Basically, if you make aluminum, you get the gallium. If you make copper, you get tellurium or cobalt. If you do lead and zinc, if you do lead, you get bismuth. If you do zinc, you can get some gallium, germanium, and indium, and so forth. And so if you control the primary production of the major metals, then you get the minor metals as well. And so that's why when you look at the gallium, 99% of the world's gallium comes out of China. It's because they dominate alumina, not aluminum. Well, they did dominate aluminum as well, but dominate alumina production because that's the processing step where you get it. Critical minerals and materials. I thought Tom did an excellent job. I now saw him walk into the room, so Tom, you did an excellent job. Thanks. You're my boss. Give me a raise. So why do we have two lists? And I think for those people maybe on the outside looking in, you get very confused because you don't understand why we have the different lists that we have. Tom did a great job. I'll give you my slant on this, right? USGS focuses on domestic economic. That's important, domestic economics. So you can see on the x-axis you have disruption potential. They grade it from 0 to 1. What do you think the likelihood of a disruption potential is? And you can see that samarium, that green circle at the very bottom right, the likelihood of a supply disruption is high. Why? Because it's all pretty much produced in one location. Okay? Then we have, on the y-axis, economic vulnerability. That means if there was a disruption occurring, we'd have a huge economic. So obviously, the impact on gold and copper and aluminum, high tonnage metals, if there is a disruption of those things, the economic vulnerability would be high for us because we use a lot of it. Okay? And then our trade exposure is the size of the circle. So the bigger the circle, the bigger that we import. And so the biggest circles are 100% import. They essentially multiplied those things together and took a geometric mean, and the highest number became red, so cobalt and gallium. Okay? So gallium is number one concern for USGS, and so for young researchers, it's about who you know, it's not what you know. If you want to know why I have a project in gallium, because I called Nadal Nasser, who's the first author on this, and I said, what element are you worried about? And he said, gallium. I said, okay, let's go find gallium. I was not smart, I just knew the right person to ask. So, gallium, we don't talk about niobium, but niobium is number 2. Why is niobium on there? Because there's one mine in Brazil that has 450 years worth of the world's supply in it, and who owns that one mine owns the niobium. So Tom mentioned about semiconductors. If you go do an AI search on what materials do you need for the future of quantum computing, I need superconductors, and niobium's on the list. So all of a sudden it becomes just an element that I use for steel, high-strength, low-alloy steels, to superconductors. So should we be looking at niobium because it's high on this list of concern? But right now, it's not high on anybody's list that I know of in the federal government being funded. Then we have the critical materials assessment. Notice this is not a list, this is an assessment, okay? And if you go back and look at the wording, it's a world perspective. It is not a domestic perspective. This is DOE's assessment, and when they did this, was in the world total, are we worried about the supplies of these elements? Not necessarily domestically. This is just worldwide, okay? And the critical material list by DOE is not created by this assessment. It is created by the Secretary. And so when the Secretary announced earlier this year that metallurgical coal is now on the critical material list, notice it's not on the assessment at all. It doesn't have to be on the assessment. The Secretary said so, okay? Dad said so, so that's it. And so there's a reason why there's two lists. And there's a reason why the Defense Department has its own list, right? In the same way, like if you're working on a company right now, there are things in your company, in your supply, in the way you run, there are certain pieces of equipment or certain supplies that are critical for your operation. As an academic professor, they're not critical to me. What's critical to me is the number of students coming in, right? Research dollars, the things I get promoted for, right? So just because there's different lists, it's because they've measured certain things about certain ways. So just have to understand that. Because CMI is funded by DOE, we do worry about this assessment. We use this to guide what we find important. And of course, we focus those things that are red and yellow in the midterm. The elephant in the room is always China. And I show these a lot, so if you see me make presentations, I apologize. I have updated them to at least 2023. And this is the elephant in the room, right? So the problem is with copper. Why are we worried about copper in the United States? Well, I mean, we produce a good amount, but we consume more. We consume basically about 1.7 million tons, and we only produce about 900,000 tons or so per year. So where do we get the rest? Well, it comes from the market abroad, and because the Chinese have built 41 copper smelters in 31 years, and we have 2, it's a big deal, okay? And this is why they dominate the gallium market, which has been in the news a lot, because you get gallium when you process bauxite into alumina and you pull it out, and they pretty much make sure that they capture gallium. So they flooded the gallium market. Gallium used to be 100 tons a year, now it's 400 tons a year, and the rest of the world just can't compete. Why did we shut down our operations? We used to have, when I started, when I was a young man, we had 12 copper smelters. We have 2 now. We do no, well, I guess we shouldn't say that. There is 2 now recycling smelters that have restarted in the last 2-3 years, one in North Carolina and the one that Rubis is building in Georgia. So we are rebuilding stuff. So why did we shut down smelters? Copper, zinc, lead, aluminum, alumina. And the short answer is we're a mining country, and so we build a lot of smelters by our mines, and as the mines played out, because mines are depleting assets, it just wasn't economic to transport things to the middle of Montana, for example. The other thing is that we don't play on a level playing field. Other countries have invested in their smeltering capacities. They consider them national assets. I was talking with a colleague yesterday, and the Australians just ponied up 120 million, 30 million, what did you say, for a zinc operation, lead operation, because they want to keep that smelter in operation. When was the last time we did that? Well, I guess we just did that. We just gave MP Material a lot of money, right? We bought into them. So maybe we're going to start doing this. The other thing is that we used to have direct contracts with people, and over time we've created commodity warehouses. So there's the LME or COMAX warehouses located throughout the world. So if you ask a materials engineer where everything comes from, it comes from the warehouse, right? And that just disincentivizes everybody to low cost. So as long as I can produce at a certain grade, I can put it there. And then let's face it, the U.S. government has actively avoided supporting the industry. So I put a few things here. There's a plot of copper there over the last 30, 40 years. There's a few arrows there for dates. I love 1984 because that's when Business Week reported the death of mining, right? Mining was going to die in the United States, not because we were killing it for social reasons or environmental reasons, it was because copper was such a low price they couldn't do it economically. And then they said the death of mining. So I was 14, if you want to do my age, I was 14 then. Fortunately, I wasn't allowed to, I didn't read that article before choosing my career. In 1996, when I did my master's, I was one of the last projects funded by the U.S. Bureau of Mines. I was in the last tranche of students, so I'm very thankful for the U.S. Bureau of Mines. But the U.S. Bureau of Mines, by the way, has not been eliminated. It's just been unfunded. The U.S. Bureau of Mines still exists on paper. The government just stopped funding it. Okay, so again, it's a mincing of words. It's effectively gone, but it still on paper exists. They defunded it in 1996. In 2011 was when the DOE did their first critical materials assessment. That's really when, I think in my mind, critical minerals or materials started to raise to my consciousness that the government had finally woken up to the fact that we weren't supplying all the materials that we needed as a nation. And then in 2017 was the first Trump executive order, which really, again, highlighted, and we've had multiple executive orders from multiple administrations since then. And so over the last, 15 years, 14 years, all of a sudden, what I do matters to the federal government. I can promise you when I became a professor in 2005, I remember going to NSF and going to the materials section, and it specifically said, no proposals on extractive metallurgy. So, okay, I guess I'm going to go to industry and find money. So for those of you in industry who supported me, thank you, appreciate that. So when we look at it, we talk about minerals, and a lot of times we focus on the mining aspects. And I know there are mining companies in the room, and I know that mining permitting is a huge problem, but I'm even more, in my opinion, the problem is the lack of processing plants in the United States. Because even if we make the concentrates, we're shipping it somewhere, right? Because we have one primary zinc smelter, we have 0 lead primary smelters, we have 2 primary copper smelters. Now, we do make a lot of Electra 1 copper, so that's a little bit mincing of words. But we just don't have the processing plants. We have 1 alumina refinery in Gramercy, Louisiana. So we just don't have this middle processing part. And if you want the byproducts, the minor elements that are really the easy things to manipulate, pain points, because the world tonnage of tellurium is 1,000 tons. The world production of gallium is 400 tons. The world production of germanium is 180 tons, right? I mean, 180 tons is 1 heat of steel in a steel mill. I can produce that in 45 minutes in a steel mill, in a mini mill, right, because it's small. So we can really accentuate the problem because we don't have the processing. And so that's really what we're looking at is how do we process domestic resources and what are the technical challenges? Now, there are a lot of economic challenges. Maybe I think Aaron's going to talk a little bit about some of the economic challenges. He and I have talked a little bit to make sure we don't overlap. But there are a lot of economic challenges. I'm not going to address those today. I'm just going to look at what are some of the technical challenges that we need to address. Anybody who's a mineral processor or a chemical metallurgist or an extractive metallurgist, this is a list that we could write about almost any metal, right? I mean, I always say when people ask me, well, what's the problem with critical minerals? I'm like, which element are you talking about? Because everyone has its own story. But basically, the needs are, I would like to maximize my throughput through existing mills. Can I ore sort beforehand, right? Can I upgrade the material so I don't put low-grade material through my mills? Because the mining guys are always screwing us and making sure that the low-grade stuff comes through, right? Excuse my language, excuse my French, okay? 3-4% of the world's energy is consumed by making big rocks into small rocks. Now, that's not mostly for metal mining. That's mostly for your gravel pits out here, your crushed rock. But still, we use a lot of energy in comminution. So are there better ways to make big rocks into small rocks? Flotation, when it was invented 100+ years ago, revolutionized mineral processing. We float almost everything, it seems like, these days. I know that we do some other types of separations. But when you look at across the board, flotation is the predominant way we upgrade our minerals. Inherently, there are problems with floating big particles and small particles, just from a physics standpoint. And so a lot of companies have spent a lot of time on that, but what can we do better, right? This is about what our needs are. If you can improve your coarse flotation or your fine flotation, you can get better recoveries. There are certain minerals that are just hard to leach, right? And so we have to get aggressive in our temperatures and our conditions. Maybe we have to go to an autoclave. Maybe we have to go to really strong acids, really strong bases. Is there something that we can do there creatively to reduce that? Many of our elements, when we look at them, and I tell Tom this all the time, what I'd really love is to find out how to get from 10 milligram per liter to a gram per liter economically. There's so many things that are running around in our process solutions that are in the tens of ppm, and they're just not economical. So is there some magical sauce? Is there some magical way to upgrade to 1 gram per liter? Because once you get to 1 gram per liter, then there's all sorts of stuff we can do, probably economically. But the problem is I need some sort of passive collection system, right, that costs almost nothing, costs no energy, so forth. If you all are thinking of a great idea, man, you are smarter than I am. But that's what I hope. Computational chemistry. One of the things that I've really enjoyed about being part of CMI is the fact that I have got to see what Oak Ridge and other Ames and Idaho National Labs gets to do in the computational chemistry. This is where AI, in my opinion, and machine learning, we have a lot of data, we have a lot of opportunities to look at, can we create new chemicals that are selectively targeting certain things to go after those things? And you can see the rest. I'm going to run out of time. I'm going to quickly go through what I think are some of the rare separation needs for specific elements. I'm going to talk about rare earths. I'm going to talk about battery materials, semiconductors, and precious metals. I already knew I was going to run out of time, so I'm not going to do copper and magnesium. In rare earths, we produce mineral sands in the southeast United States. We need a better flotation system to capture the monazite. The monazite can be processed at Energy Fuels in Blanding, Utah. They already have regulated tailing impoundments for radioactive materials. So if we could get a better grade, maybe that way we could get more rare earths coming out of that material. Rare earth separations. We all know, anybody who does separation rare earths, they're all +3. They're all pretty much the same size. They're really, really hard. And I think the real challenge is the separations for heavy heavies. So if you know rare earth seg plus materials. We still need better metallization. Tom highlighted some of the things that CMI is doing. Progress is being made in the area, but I've been to MP Materials electrolytic operation in Fort Worth, Texas. As a extractive metallurgist who sees really large plants, it's pretty small and pretty manual. So what can we do better there? And then anytime you deal with rare earths, you always have to deal with the radioactive materials. What are you going to do with the thorium? What are you going to do with the radium? What are you going to do with the stuff that you don't want? Which is always true with any hydrometallurgy. And battery materials, direct lithium extraction, how are you going to get small amounts of lithium out of the brines? That would be the cheapest way to do it. There's a lot of work going on in this area. I'm not saying that CMI is doing this, but there's a lot of work that's being in the area. But we need to come up with, again, how to get from ppms to gram per liter. For spodumene, there's a lot of energy that's involved in decrepitation of the alpha spodumene to make beta spodumene before you acid leach. So can we do that in a more energy efficient way? When you look at nickel cobalt, CMI, we don't do, it's not in our swim lane for black mass recycling. But we know that there's problems when you look at cobalt, like solvent extraction, and the manganese that's in the battery material fouling your solvent extraction. So what are you going to do about that? If you go to primary minerals, the cobalt that's at least in Idaho is always associated with the arsenic. So what are you going to do with the arsenic? And of course, I couldn't say something without saying about nickel cobalt in Missouri. The Missouri, Idaho, and Minnesota nickel cobalts are low grade relative to the rest of the world. They're very complex ores. So you're going to have a process flow sheet that handles a lot of different metals and makes values out of most of them or all of them. And when it comes to graphite, we saw the presentation from Jamie yesterday talking about graphite in Alaska. There's some natural graphite that might be able to be available. We can make synthetic graphite from a lot of different materials, but it's usually high temperature and high cost. From gallium, we need to figure out a better way to get gallium out of the bare process. We need to be something that's much cheaper. And also, if we're going to do domestic resources, all of our bauxite's subeconomic, so we need to come up with different ways to process that. We can go back after the red mud. I know that's not on the list, but there's always people looking at red mud for gallium and other elements, so we should look at that as well. we have a project here at S&T looking at gallium from the zinc plants in the United States. It's very challenging to get gallium away from iron 3. So if there's a way to do that, that'd be very useful. And then we have a lot of gallium that just is very low grade in all of our waste, all of our electronic waste. There's a lot of gallium arsenides, gallium nitrides, but they're very low grade. So what can we do about that? When it comes to germanium, we capture a lot of germanium from zinc processing already, but there are some low-grade materials that we're not processing. And so is there a way to do that? Or to go back and look at old tailings. Again, I don't remember which USGS talked about Tar Creek. I think that was maybe Jamie. You guys I know you have looked at and we've partnered a little bit with USGS, so we know what some of the germanium grades in the Tar Creek deposits or the chat piles in Oklahoma are, so that would also be something. Platinum, we are just not blessed as a country. So I don't know if this is actually a separation need, but geologists need to go find some platinum. You guys got to do a better job. And basically, I think we need to treat platinum like it's a national resource. Anytime we import platinum, palladium, iridium, ruthenium, everything has to be recycled. Everything. I know in iridium space, there is stuff that comes in and that's used on dimensionally stable anodes that are not recycled because it's not economical. So in summary, this is the same list, but kind of maybe reprocessed or rethought of. So improving rare earth separations, especially the heavies, improved metallization, thorium sequestration or removal of radium from phosphogypsum, so dealing with naturally occurring radioactive material or NORM. Battery materials, we really lack good domestic resources of nickel, cobalt, and graphite, so we have to kind of come up with individual processes for what we have if we're going to do it domestically. The energy consumption for lithium, whether it be direct lithium extraction or from spodumene. When it comes to manganese, I didn't really say that. There's excessive electrolytic manganese in the world. The Chinese have really flooded the market. So I was happy to see when Pat talked yesterday about making manganese as directly to a chemical instead of to electrolytic manganese. I'm wishing they're successful. I'm hoping they're successful. And for semiconductors, it's, again, looking at different places to get gallium and germanium. We are also doing work in tellurium. It's lower on the critical material list. That's not funded by CMI. And again, with PGMs, we just have to do that. So those are all the needs. My question is, who's going to do it? I mean, the whole point of this, over our thing is workforce. And if we aren't bringing the people in the front door, so if you think the problem with getting people into mining is difficult, try to get them into metallurgy, which they can't even pronounce. So, we struggle with that. We all struggle with getting people in the front door. This is Dennis Proteus, who's my deputy lead at Ames in the CMI. We all have to do our part. We know we have lots and lots of data to say that people come to metallurgy or ceramics or mining because someone told them about it. Someone said, oh, you're bright. You should look at this. So today my call of action to you is please go tell your nieces, nephews, neighbors, friends about the awesome field that this is and to ask them to consider looking into it. Thanks, and I'll be happy to answer any questions.